Connection between sines and chords of circles goes back to ancient astronomy. Early astronomers were interested in chords of circles because they thought planets moved in circular orbits. The Greek mathematician Hipparchus wrote a treatise on chords of circles around 150 BC. This work is now lost, but many of the ideas survived in the Almagest, written some 300 years later by Claudius Ptolemy. The Almagest ranks with Euclid's Elements as one of the great masterpieces of ancient times. Both were written in Alexandria, a magnificent center of Hellenistic culture, a city founded by Alexander the Great after he conquered Egypt in 331 BC. In the Almagest, Ptolemy derived a basic formula for the length of a chord cut off by the sum of two angles. We can discover this formula ourselves from the property of chords of circles discussed earlier. Remember, in a circle of diameter 1, the length of any chord cut off by an inscribed angle is equal to the sine of the angle. So, if this angle is A, the length of this chord is sine A, no matter where A lies on the circle. Similarly, if this angle is B, the length of this chord is sine B, no matter where B lies on the circle. Now, bring the two angles together at a common vertex. They form a larger angle, A plus B, that cuts off a chord whose length is the sine of A plus B. To find the length of this chord another way, drop a perpendicular to the chord. It divides the triangle into two right triangles. The base of this right triangle is its hypotenuse times cosine B. The base of this one is its hypotenuse times cosine A. Putting these together gives the addition formula for sines. It says, the sine of A plus B is equal to sine A times cosine B plus sine B times cosine A. It tells us how to find the sine of a sum in terms of sines and cosines of the individual parts. Ptolemy himself proved the addition formula in another way, using a remarkable property of quadrilaterals that can be inscribed in a circle. A quadrilateral is a polygon with four sides. Not every quadrilateral can be inscribed in a circle, but for those that can, the product of the lengths of these two opposite sides plus the product of the lengths of these two opposite sides is equal to the product of the lengths of the two diagonals. This equation is called Ptolemy's theorem, and it can be interpreted geometrically in terms of areas of rectangles. The equation is true no matter where the vertices lie on the circle. Now let's see why Ptolemy's theorem is true. These two angles are equal because they cut off the same chord. Rotate this triangle until this diagonal of length E lies along this edge of length B. The two shaded triangles are similar. Likewise, these two angles are equal because they cut off the same chord. So rotating this triangle reveals another pair of similar triangles. If we rotate both triangles, we see that they join along a common side that divides this diagonal of length F into two pieces of lengths X and Y. Now we have two pairs of similar triangles, so ratios of these corresponding sides are equal. And ratios of these corresponding sides are equal. And the rest is just a little algebra. The final result is Ptolemy's theorem on quadrilaterals inscribed in a circle. Let's see what happens when the quadrilateral is a rectangle. These two opposite sides have equal length. These two opposite sides have equal length. And the two diagonals have equal length. Surprise! Ptolemy's theorem becomes the Pythagorean theorem for right triangles. The sum of the squares of the legs is equal to the square of the hypotenuse. Now we'll use Ptolemy's theorem to derive addition formulas for both the sine and cosine. Start with the circle of diameter 1, take angle A, and form a right triangle. The lengths of its legs are sine A and cosine A. Use angle B to form another right triangle. The lengths of its legs are sine B and cosine B. The two triangles together form a quadrilateral inscribed in a circle, with one diagonal being a diameter of length 1. The length of the other diagonal is the sine of A plus B. Now apply Ptolemy's theorem. The product of the lengths of these two opposite sides plus the product of the lengths of these two opposite sides is equal to the product of the lengths of the diagonals. Presto, the addition formula for sines. To get an addition formula for cosines, first rotate this right triangle 180 degrees, so this diagonal is a diameter, and this triangle is a right triangle. The length of this leg is the sine of A plus B, so the lengths of this one must be the cosine of A plus B. Again, we have a quadrilateral inscribed in a circle, so we can apply Ptolemy's theorem. The product of the length of these two opposite sides plus the product of the lengths of these two opposite sides equals the product of the lengths of the two diagonals. When it's written this way, the result is the addition formula for cosines. It says the cosine of A plus B equals cosine A times cosine B minus sine A times sine B.